Okay, thank you. Sorry for interrupt.
Okay, thank you. Thank you, Henry's introduction. Hello, everyone. I'm Jun Chi from Fudan University. Previously, I got my PhD from Georgia Tech this year. My lecture today is about the quantum machine learning. The topic is about from theoretical foundations to applications on NISQ devices. In this lecture, I'm going to cover two important topics. The first one is just an introduction about this quantum machine learning on these Q devices. I will show the related backgrounds and maybe introduce why we are motivated in this research from the classical AI experts to these quantum machine learning scientists. The second one is I want to introduce our related new work about theoretical foundations of variational quantum circuits. Maybe it's cover two topics. One is we show our research work about this variational quantum circuit-based quantum neural network. Then I will show the future work about the pre-trained models for classical quantum transfer learning. Okay, let's get started. The first one is about the related backgrounds of quantum machine learning. It's a too big. Before I want to talk about this quantum machine learning, I'm going to show some classical deep learning. Previously, I'm doing this deep learning applications. What's the secret behind this deep learning for in nowadays machine learning applications? There are two main factors to pushing the machine learning or deep learning forward. And the first one is we have a very powerful GPU hardware. And the second one is there are large amount of training data. The powerful GPU hardware is enable the model bias to the training data lower to zero, and the big data can reduce to model variance to test data to a small scale. So many people can describe the deep learning as alchemy because we don't care about so much about this deep learning theory at all. Instead, we might focus on engineering tricks. Maybe so we can choose memory model architectures. It's a fully connected, convolutionalized. Maybe you use whether or not we use a recurring architecture. Other people maybe think about maybe use a different optimization algorithms to maybe improve this efficiency of deep learning training. Regularization is also important because we can use some batch normalization or data augmentation to further improve the performance of deep neural network. But my PhD work is a little bit different. I do a lot of work about the theoretical understanding about this deep learning theory. What's one difference between the classical machine learning and the deep neural network is that deep neural network is a very difficult, it is very easier to jump out of the overfitting areas. It means that if we want to set up, we can set up this deep learning as an over-parameterized neural network, we can have a way to get out of the overfitting area. It means that even the data is quite large, if we want to set up the model as over-parameterized setting, it's very closer to the training data. Is a model, this performance of this very large model deep neural network can push the test loss to become smaller and smaller. We don't get into the overfitting area. This the one major difference between the classical machine learning and deep neural network. That's why there's so many engineering work maybe pursues to get a very large model, not size model, such as GPT-3 or some BERT model. But difficulty is that the hardware support is not powerful enough to support this the development artificial intelligence based on deep neural networks. And for each 18 months, this the number of model parameters for deep neural network can be increased by more than 35 times. But for the CPU or GPU development based on Moore's law, maybe it's for every 18 months, the computational power can be double. So maybe there's a big gap between the software and the hardware. So how to fill the gap? I'm motivated in our group to do some quantum computing, maybe use of quantum computers to fill the gap. So this is the motivation which we just want to do some use the quantum computing for machine learning. But major reason is that for the classical development of the hardware, it's very difficult to support the development of the artificial intelligence. So this figure shows the gap between this the deep learning development and the Moore's law. So this so in our work, we want to use the theoretical study of a classical deep neural network to put forward the quantum neural network. But for the classical study of the deep neural network, maybe for some engineers at Google, maybe other engineers at Amazon, they don't care about this the theoretical study about deep neural network. It's because they think this is alchemy. It means that we have a national amount of training data. We have a set it as our parameterized deep neural network. We only pursue this empirical study, empirical improvement. We don't care about why it can work so well. But there's some previous theoretical study can help to put forward the quantum neural network, because currently the quantum neural network is still in the early stage, because the theoretical study and empirical study in the same pace. So we can just borrow some theoretical study from the classical deep neural network to help to put forward this the empirical, both empirical study and theoretical study of for this quantum neural network. So one day maybe the quantum computers can scale to NISQ. Because NISQ, maybe they have the same, and we have the development for the two aspects can in the same pace. So it's my work is doing some theoretical study to help to put forward empirical study of quantum neural network. Okay, there's some backgrounds and motivations about quantum computing for machine learning why we chose this topic, because previously I'm a classical deep learning scientist, but now I'm all in the quantum machine learning, because I think there's so many interesting work I can do, and want to also we can fill the gap between the hardware and software. Okay, then that's just a brief introduction to the quantum computing nowadays. Different companies have different architectures for the quantum computer. IBM or Google, Amazon, so OnQ may have their unique quantum computers to want to set up their different roadmap for development of quantum computers. Maybe the typical roadmap is from IBM. Maybe this year they release 433 qubits quantum computers. Next year, they plan to release more than 1,000 qubits. And maybe in 2025, maybe they have reached a number of 1 million qubits and beyond. So this picture just shows currently we just line the domain of near-term quantum computers, because currently we have access to about as much as about 400 physical qubits. So now we just it's in the NISQ device, and in the NISQ era. About 3 or 2 years ago, we just in the very early stage, because at that time we only have a 10 to the 100 noisy qubits. But now we just jump out of this domain, so we just in the NISQ era. But we have to wait for so many years before we can get this 4,000 quantum computer. With a 4,000 quantum computer, it requires more than 1 million qubits. But now we don't can have about 100 or maybe 400 NISQ queries. But for such area, we have many applications nowadays. For example, it's a quantum machine learning is one typical application example in such a NISQ area, because for the requirements of quantum machine learning only requires about 40 physical qubits. Maybe it's next year, maybe it's in 2023. So many machine learning tasks can be conducted by using quantum computers because they have very low requirements for such as for many machine learning tasks. But if we have more than 400 NISQ qubits, vast majority of machine learning tasks can be conducted. But for many other tasks such as finance and then this diffusion, solar conversion, even some drug discovery, maybe have wait for more times. It takes more than 5 to 10 years to accomplish such a task, because they need algorithmic qubits more than 200. It's a very high requirement for current quantum computer to reach. So, but that's why I'm motivated to the quantum computing task, because it's easier to realize on the NISQ device. Maybe the next year, vast majority of the quantum machine learning tasks can be conducted, can be realized. Okay, that's a roadmap and introduction of the quantum computers on NISQ device and why we chose the subjects of quantum machine learning. Maybe it's also this for total quantum computing is inspired, but nowadays we have the noisy intermediate scale quantum device. So, but it doesn't matter because quantum machine learning has a very low requirements for the physical qubits. Okay, so from last year, we have several workshops and some conferences to show, to maybe want to show our interest in such a domain. And we just invite several guest speakers and organizers to give some related talks about its quantum neural networks for machine learning applications. In our previous domain, we just focus on our speech and natural language processing. So we just found very familiar topics from the speech processing. I think we just generous to other domains such as computer vision and natural language processing, maybe used in biology. So this year, have an ICAS conference. We invited several groups focusing on the quantum computing to submit some papers from our group, from University of Georgia Tech, from Johns Hopkins, Cambridge, and Virginia Tech, and companies such as Wells Fargo, Google Green, and IBM Research. So maybe it's next year, as we will invite more research institutes and universities to join our journey about this quantum computing for machine learning. Okay, just a brief introduction to the quantum computing and our work about this quantum machine learning. Next, I'll just show you two paradigms. Maybe the two main stream paradigms in the domain of quantum machine learning. The first paradigm is quantum kernel learning. It's commonly used nowadays, but not our interest. Okay, but I just want to touch upon a little bit about this topic. The quantum learning formulation just are very similar to the classical kernel learning formulation. Because it's very similar to the linear classification, and then only one difference that the kernel, how to define the kernel, how to compute the kernel. We just don't use some Gaussian kernel and by the classical computing to get its Gaussian kernel. Instead, we want to use this quantum computing to get a kernel. We just if there is a point in this input space, we want to use a quantum mapping, quantum computing to map to find this quantum feature in a quantum variable space to get a quantum feature. and want to use a quantum feature, use a quantum circuits. It is a quantum circuits to get to compute the quantum kernel. If we repeat this process, the computing process are many times, maybe it's the practical kernel result very close to the mathematical one. This is the basic idea about quantum kernel learning. But for the classification task, quite related to classical kernel learning. So if you want to compute after computing the kernel architecture and kernel formulation, then we can use the classical classification to do a pattern recognition task. So maybe there's a nowadays, we can use a quantum kernel learning to realize some state-of-the-art performance. It's very compatible with the most classical machine learning task. Because we do only one thing, we use a quantum computer is to how to compute these kernels. It's how to compute the quantum kernels. And if we use quantum computing, the computational complexity can be reduced from n squared to log n. It's the most advantage and quantum advantage of using this quantum computing to compute this quantum kernel. So many people are very interested in domain and use such as quantum kernel learning for pattern classification. But in our work, we're more interested in another domain is based on the variational quantum circuits, because there's so many unknown, unresolved problems in such a paradigm. But for the quantum kernel learning, is quite mature now. So even quite mature is more engineers in the industry more welcome to this domain. But for expert and for expert in academia, we are more interested in unresolved problems. So Ms. Currently, in our work, we are very interested in variational quantum circuits. So maybe it's in 2019, we are the first one to propose this variational quantum circuits for quantum neural network. Previously, there are so many quantum neural network paradigms, but no one can really be conducted on real quantum computers. But we are the first group to just release this variational based quantum circuit. This consists of about 3 parts. Maybe the first part, we call it the tensor Fudan encoding. It's just want to convert the classical input data into the quantum states. The second component we call it the parametric quantum circuit. It just allows the quantum states go through this the parametric quantum circuit. The output of this component is the output quantum states, and then we just do the measurement. The measurement is observable as a Hermitian operator in the output quantum states to get the result in the classical domains. Okay, there's a question about how many qubits in this Q device. Okay, it's you realize what kind of quantum computer resources you can get. For example, you can get connected to IBM devices, a quantum device. Maybe you can use a 34, or you can use as much as 34 qubits. But at that time, in 2019, at that time, we only have about 10 qubits. For this task, we'll have only about 10 qubits. So that's why we just use it for the reinforcement learning instead of other very complicated architecture, because we have a limited number of the qubits, available qubits to set up as a quantum neural network. That's also why we just use the variational quantum circuit instead. So this is a training process of variational quantum circuit. It's straightforward. It's just an interaction between CPU and the GPU. And the CPU just control the learning rate. When it's going to stop is the training process. And the GPU just store these quantum circuits and just outputs the measurement, just give feedback to the CPU. So this architecture is as an example about this PQC. PQC is a parametric quantum circuit. It's just a unitary linear operator transform the input quantum states into the output quantum states. And the measurement is very important because uncertainty about this quantum mechanics. We have to do so many times, about 1,000 times measurement, and just based on this Hermitian operator, Poisson operator, to just to get the cascade result, and cascade result just we take the expectation, because every time there has some probability to get one result, but the final result is an expectation about at least 1,000 times measurement. So maybe it's after the 1,000 times measurement, that the expectation value can be stable. Otherwise, maybe it's quite random to get one result. So we use the expectation value as the castle outcome to further do the classification or the regression task. Okay, this by using such a variational quantum circuits, we don't at that time, because we only have 10 qubits, so we just do some simple deep reinforcement learning task. At that time, this is a very easy task from the current perspective. And the codes, maybe at that time, our codes have been released and get the first prize in Shenandoah AI quantum competition. So this is very pioneer work. The architecture very simple. We just want to replace the deep Q learning architecture with a VQC circuits. So instead of just using deep Q learning, we just replace it with the architecture here. Okay, so you use such architecture to reduce so to replace the deep Q learning architecture. But other training paradigms maintain the same. They keep the same. So we just want to simulate such as environment based on the thousand snake environment. And at that time, I only consider this a very simple task. But this for this task, we can use a dynamic programming to perfectly resolve such a problem. But at that time, we want to use a deep reinforcement learning based on variational quantum circuits. We want to discover whether or not such as a paradigm, quantum paradigm, can resolve such a simple task. But our discovery result to show that to find that after many about 300 episodes, maybe the results can be converted to the best one, the best outcome. So our conclusion at that time is that it's feasible to use a variational quantum circuits to replace the deep Q learning architecture for some machine learning tasks such as reinforcement learning. After that, in 2020, we want to use this architecture for speech recognition. At that time, only because at that time only have about 10 physical qubits. So instead of just replace the QuCS model for speech recognition, we just use some these 10 qubits to set up the quantum convolution layer to extract the speech features. So instead of to let the input speed feature go through the QuCS model, this QuCS model is end-to-end architecture. Instead, we just let these speed features go through this NISQ server. In this server, we want to let the features go through this randomized quantum convolution layer to get the speech and the quantum encoded speech features. That use such a quantum encoded speech features to as an input to feed in this end-to-end architecture. Okay, this is the basic idea about the illustration of a quantum convolution neural network. All the parameters for these architectures for the quantum case are randomized. But for the input, maybe we use the Mille spectrogram of speech to encode it. There's an input rotation case, but uses And the output is that this quantum encoded speech features. And our picture, there's a comparison between the different results about speech features. And the input is a mere spectrogram, and the figure base that use the classical convolutional encoding features. And third one is the quantum convolution encoding features. And we can find that is the quantum convolutional encoding features is becomes more discriminative than the classical convolutional features, as more discriminative than the classical deep spectrogram. And the related experimental results also just correspond to verify our observations. So we can see that if we use the quantum convolutional encoding features, we can achieve the better result compared with other baseline results. So at that time, we will see that we can see that if we use a quantum convolution layer, maybe just to get some speed features in the quantum Hilbert space, the features become more discriminative than the classical features. This is from the perspective of empirical study. So this is what the early work at that time. Okay, but there's some bottlenecks about the frequency-based quantum neural network models at that time. One major difficulty about the frequency-based quantum neural network is that the whole transformation is very unitary. It means that this model has a limited representation capability. The second problem is that the optimization problem. We in quantum machine learning we call it a barren plateau. The barren plateau can be described as this thing that ideally we want to find is a path from the bottom of a mountain to go through. To find one path to go to top of mountain is ideally, but in reality, we want to do some optimization task always in the horizon line. So we can't find this path to come up the mountain. So this is the bad thing. So we call such a problem as a barren plateau. So how to overcome such as disadvantage of frequency-based quantum neural networks? So we just propose a new architecture. We call it the tensor twin frequency or TTN frequency. And this work has been shown in our NPG paper. Maybe it has been accepted yesterday. So in this work, we want to just overcome these two major disadvantage for the variational quantum circuits. The first one is how to boost the representation power of the frequency. And second, how to avoid the barren plateau problem. We want to do the training process. Okay, so just next, to do some to show our theoretical foundations of the variational quantum circuits. Okay, it's just a focus two problems about this inherently existed in this frequency-based quantum neural network. Before we show that, any question about it? Okay, if no, they want to just go through this the second lecture, the second part. So in this part, I have to show our recent work about the TTN frequency. So let's recall that for variational quantum circuit, there are three components. The first component is just tensor product encoding to convert the cathode input data to the quantum states. And the second part is the parametric quantum circuits. It just it involves so many adjustable quantum qubits to fine-tune the model parameters, and that's why I do the measurement. For our new architecture, it's a little bit different. Before this classical data feed into the vacuum-C model, we want to introduce one tensor twin layer to pre-process the classical data. Why should we introduce that as a tensor twin layer before the vacuum-C architecture? because we want to introduce the nonlinearity in the Hilbert space for the conversion between conversion from the CASA data to the quantum states. So because this for the vacancy, there is a unitary linear operator, so it doesn't have the nonlinearity in the vacancy architecture. But for very complicated target function, it's very difficult for this vacancy to approximate with this target function. So how to resolve such a problem? We want to introduce the nonlinearity to this vacancy architecture. How to introduce such as a nonlinearity? We just introduce one layer, it's a one tensor train layer to do that. So in the feature space, we just add some nonlinearity in the Hilbert space for the further tensor product encoding. And the next work, we want to mathematical analysis is the test error in terms of the sum of the representation error, estimation error, and optimization errors. Okay, to begin this mathematical analysis, I just show this what's a tensor train network. Maybe in tensor train network in physics, we also call this the matrix product network. Okay, so maybe have a different name, but in machine learning, we'll call it a tensor train network. Our principle to show this tensor train network provides a compact tensor representation for neural network. So given is the feed forward with dense layer, maybe just a two-layer feed forward neural network, we can just simply to convert such a problem to this dense layer into the tensor train layer. So instead of just only one two-dimensional matrix, we consider several the tensor parameters. Tensor parameters can be trained during the training process, and the input is not as a vector in a multi-dimensional tensor. So for such architecture, our speech recognition or speech enhancement task will show that the tensor train network can maintain the representation power of a neural network, the classical neural network, from the perspective of empirical study. More importantly, this architecture for such a tensor train layer can physically find an equivalent quantum circuit, and can be conducted such architecture and such a model on real quantum computer. So this figure shows that for this it's a matrix product state. Matrix product state just tensor train layer is one layer. So maybe this can use the quantum circuits to realize such as the classical tensor train layer. So even if we have more than 100 qubits, or maybe so 200 qubits, we can just use 100 to 100 qubits to realize the tensor train layer. But for classical neural network, it's impossible. It is intractable to use a quantum circuits to approximate the dense layer. But if you want to convert the dense layer to the tensor train layer, so we can use 100 qubits to realize the quantum circuits to approximate such a tensor train layer. So this we call this such architecture as an end-to-end quantum circuits, a quantum neural network. Because from the very beginning, it's a tensor train network. We can use the quantum circuits. But variation quantum circuits needs totally quantum circuits. So this architecture we also call this end-to-end quantum neural network without involving any classical neural network. So this why we just introduced the tensor train layer in this work. The most important reason that we want to by introducing such a tensor train network, we just involve some nonlinearity in the Hilbert space for the tensor product encoding. A second one is that the performance. The tensor train layer can maintain this. The tensor train layer can maintain the performance of classical neural network. For such architecture, we can use some classical neural network to do this the data processing. For example, the data dimensionality reduction. But why we choose this tensor train layer, because it can use the quantum circuits to realize this end-to-end quantum neural network. So all the models can be realized by using the quantum models instead of involving any classical neural network, classical models. Okay, the next step, I want to do some mathematical analysis. We just focus is the QuCS representation power and the generalization power, and we want to see his how to boost his optimization performance. So this I'll just show our theoretical result. The first theoretical result is focus the representation error for this QuCS-based neural network. And in this result, we will show that it's quite related to the two main factors. The first factor is a number of qubits. The second one is a counts of the measurement. So these are the representation errors is inversely proportional to this number of qubits. Also is inversely proportional to the counts of measurement. Our some experimental study want to corroborate our theoretical results. It will show that if we use more qubits, the ME loss can be reduced significantly. Just very tightly correspond to our theoretical results. Okay, this the representation power that's co-associate with the representation power and expressive power of such as a QuCS architecture. If we use the tensor train layer where the nonlinearity is introduced. The second one is about that focus on estimation error. Estimation error just closely related to the generalization power and generalization capability. And here is quite related to this model complexity, is the model complexity of QuCS. And another thing is that it's amount of training data. So here we just want to collect more training data. The more the better, because we see that the training data is in the denominator place, and so we still have more data coming with the training errors, maybe it's estimation error. Also we can call it a training error, and it can be reduced to a small scale. But the problem here is that for the optimization error, we want to we could see the number of model parameters very closely related, being close to the number of the training data. So this contradiction between this setup about this QuCS. On one hand, we want to the more data, and on the other hand, it's difficult to set up very even over parameterized QuCS. So in our experiment, we just see to set up as a PL condition. PL condition is that and maybe it's one simple case is that it's a model parameters of QuCS is very close to the number of training data. If such a conditions can be met, so we can see that it's very easier for our QuCS to get a well-trained QuCS. So maybe, but if you do have such a setup, maybe the test loss maintain a very high level. But you have this other condition, the PL condition, can be met. Maybe the test loss can be close to a small scale. So just the trick. How to set up the QuCS model, how to optimize it. If this PL condition can be met, it's easier for us to get a well-trained variational quantum circuit model. But the difficulty is how to set up such a PL condition. And the PL condition is a sufficient but no necessary condition to avoid the problem barren plateau. So for such this result, why this line cannot lower to a small scale, because it's just in the stay in the horizon line. You can't find a path to come up the mountain. So this why this the result is still stay in the high level. It doesn't reduce to a small Tesla loss. But the problem is that the PL condition is sufficient and not necessary to avoid the problem. So how to set up our proposed TTN frequency model to satisfy the PL condition is still in the investigation. And the second existing problem that with a more available physical qubits, maybe it's necessary, maybe have more than maybe some 1,000 qubits. We can use that more than 1,000 qubits. If it's more qubits come in, it's more difficult to overcome the problem of barren plateau. So these are still two existing problems in our paper. How to further improve it? So in our engaging a new paper to further improve our existing work. In this new paper, we consider a pre-trained model, or maybe it's a pre-trained classical model or pre-trained quantum model for further improvement of the tensor train frequency model. So pre-trained model architect and this technique is currently very popular in classical deep neural network. Maybe the one last week is the ChatGPT-3 or ChatGPT coming. With previously there's a GPT-3 model and the Bohr model. That's all pre-trained model. If you have this universal pre-trained model for some specific task, maybe it's a certain task, it just fine-tune some classifier and maybe to realize a different machine learning task. So we also want to use a pre-trained model for such a task to resolve these currently existing two problems. The one is about how to set up the PL condition. The second problem is that if there's more qubits coming, maybe it's even we use a pre-trained model, whether or not with the training, the optimization process become easier. So this is the second work we want to investigate. We want to use the pre-trained model for further improvement of the frequency-based quantum neural network. Also, we call it such an architecture, we call it the classical to quantum transfer learning. Or we will call it the classical quantum neural network. Okay, this is some introduction about this meta-learning, always very similar, very popular, very hot topic in classical neural network. Maybe you can imagine the pre-trained model as the GPT-3 model with the Bohr model, transformer model. Anyway, maybe it's DA, but anyway, it's all kinds of different variants of GPT-3 model. And maybe the data, maybe coming data is just maybe it's from different sources, maybe from different tasks, maybe the test data, image data, speed data, or kinds of different data. What I want to do is that we want to have this universal representation to different kinds of target to source data. After we train this get a pre-trained model, for specific tasks, it just adapt to different specific target tasks. For example, if it is want to do some question answering, we just collect some the target data from this task. We want to set up some neural network, very small layers of neural networks. We just fine-tune these feed-forward neural networks. So maybe it's, by using that get connected to pre-trained model, we can just very easy for us to get to realize such a task. So this is meta-learning based on the pre-trained model. So in our work, okay, this result showed is if you use a pre-trained model, it's easier to get a better performance compared with the one to train such as the model from scratch. So this so that's why so many people said that if you have some pre-trained model, maybe some machine learning task, machine learning research in NLP or speech, maybe it's no use because we will use a zero shot training. We can just type in some sentences, some questions. Maybe it's a ChatGPT give you human-like answers. So maybe so there's no use to set up other some deep learning architecture from beginning. So maybe just use some pre-trained models, okay. But in our quantum computing learning, is that we just want to use a pre-trained model to overcome the training problems existing in our previous work. So it's a little bit different, but the source are very similar. So we're still in the investigation of this work, but our existing work has maybe it's a found empirical study about this two. The last year we have a ICAS paper about speech recognition. We just follow such architecture. So maybe just source data to get is a Casco, well-trained Casco CNDN model. And we want to borrow this one part of this the Casco model to this quantum Casco model, the hybrid quantum Casco model here. The CNN model can be seen as a pre-trained model, and we want to set it as a frozen. We want to let the same model to take part in this fine-tuning process. And the only adjustable parameters for the hybrid quantum Casco model is a frequency parameters. So there is the target data coming. We just fine-tune this the QM model instead of the pre-trained CNN model. So there's a basic architecture about this how to use a pre-trained model to further improve this quantum architecture. So there's the specific components of speech recognition for speech recognition. So maybe there's a CNN framework. It's based on Casco convolutional 1D convolutional neural network plus the Bayesian normalization plus the rule, followed by some max pooling. There's only one difference that we just want to replace the DN model with a QM model. So the first one is just a Casco model, and the second one is a hybrid quantum Casco architecture. So in this work, we want to our result demonstrates that you want to use such the pre-trained model to feature extraction or feature representation. And the accuracy of the new model is very compatible with the Casco one. Training from this Casco one is trained from the scratch. But you want to just set up the same model with a QM model and want to train it from scratch. Maybe the port accuracy is far below the baseline performance. But if we use this same model, it can be seen as a frozen pre-trained model. Maybe the accuracy can be even better than its baseline of the Casco model. So these are from this experiment, our observation is that the pre-trained model can be very helpful for the improvement of this the training of quantum architecture. So this motivates us to investigate if we use this pre-trained model, we can be better or effectively resolve such a problem. Maybe it's one assumption that if we use a training model, you use a pre-trained model, maybe it's easier to satisfy the PL condition. And the second that if we use pre-trained model, we will use a very small number of qubits. We have very powerful feature representation. So maybe use a small dimensionality feature representation. So we go through the frequency classifier. Maybe it's in the quantum Hilbert space is quite discriminative. So maybe it's just want to investigate in theory about this aspect. Okay, but for our current empirical study, we just to partially demonstrate this correct assumption. Okay, but in future we want to investigate the theoretical foundations. So we want to lay the solid understanding why this pre-trained model can be very helpful to improve this performance of frequency-based quantum neural network. Okay, that's a brief introduction to this pre-trained model for this quantum neural network. Our future work also involves some other aspects. The first one is the want to highlight the quantum advantage for machine learning. Why if we use a quantum machine learning, what's our advantage compared with the classical one? So we want to do the work from three different aspects. The first one is about the robustness against adversarial example. If we use a quantum architecture, we use a quantum neural network, whether or not if there is a classical adversarial example come in, maybe it's more robust to overcome these effects of this adversarial example. The second one is there are so many NP hard problems in many machine learning tasks. For example, in computer vision, NLP, there are so many the NP hard problems. Whether or not we can use the quantum computer, how to convert such NP, how to resolve such NP hard problems. Maybe it can be accelerated into super polynomial problems. Because there's so many ones. Okay, the third category is about the stability and efficiency of quantum reinforcement learning. There are so many theories in such domain. And also interesting some use of the quantum optimization algorithms and the current quantum machine learning in finance. Maybe some more, you see there's more demanding requirements in some of the financial sectors. So maybe it's in finance, all things very promising. The third one is quite related to Julian and Henry's work. This is about how to accelerate the efficiency of the quantum machine learning. But my suggestion is that you can consider about using Julian language. Okay, we can consider this aspect. Use a different programming language instead of instead of the Python. Maybe it's everyone knows that in this decade, the Python is quite popular in machine learning. Every scientists, researchers are very would like to use Python to everything. But for the quantum computing, I think in my understanding, Julia maybe is alternative language, a better alternative language compared with the Python. So maybe if you want to further improve this efficiency of quantum machine learning, maybe it can change to a new language. Okay. Okay, that's my talk. Okay.